As you heard, I'm Director of Quantum Computing Services. So basically, I spend half my time helping companies use quantum computers for interesting use cases, and the other half, helping them get ready for the threat. So promise and threat. And the threat is really what we're going to be talking about today. I also get to host the Post-Quantum World podcast, if you want to check it out. We often cover this topic on there with different guests, like we had NIST on, actually. And the reason we had NIST on is because on August 13th, they finally gave us the new post-quantum cryptographic standards. And that's the first round of them. Okay, so we're expecting to get future rounds, as we'll see. But the first round was released, and this will actually kick off a bunch of industry actions that we'll look at. So the two most popular that we expect folks to migrate to are ML-Chem and MLDSA. Now, you've probably heard of these in their older names. You probably heard of Crystal's Kyber leading up to this moment, and you probably heard of Crystal's dilithium. And based on those names, you know that a lot of nerds are involved in cryptography, and we like to mix Star Trek and Star Wars lingo in. But basically now they've been reduced in their coolness to ML-Chem and MLDSA. And the L in both of those is lattice-based, and we're going to talk a little bit about lattice-based today, which is really the first primary new post-quantum technology. Those are the ones we expect. Because we're limited in time, we're mostly going to focus on what's called a chem, or a key encapsulation mechanism, the actual way you try to secure transmissions. We're not going to dig into signatures today. So there are different types of PQC that are coming. Remember I said there's going to be future rounds. So some of the theoretical types that are quantum safe are isogeny-based cryptography. So while elliptic curves are not post-quantum safe, this idea of doing math between networks of curves is safe. So that's one thing that's coming down the pike. Cyc was one of these, if you've heard of the algorithm Cyc. Hash-based, most people are familiar with in general, so no need to really dig into that. Multivariate cryptography, that's where instead of just something like x cubed plus x squared plus x, you're talking about different variables, multivariables, multivariate. So x squared plus y squared plus z squared. That kind of math gets really tricky, so that helps protect systems. Code-based cryptography is going to be interesting too. That's this idea that you have error-correcting code, and your private key becomes the error-correcting code, and then you publish like garbled code, and then that way only you can reverse it and get what's behind it. And of course, lattice-based cryptography, which is what we're talking about. So what is a lattice? So simply, a lattice is a field of dots, right? And that's not very hard to imagine if you've ever seen a bullet journal or whatever, or grist. But they're not random. So we're going to get to in a moment how they're created. But this would be a two-dimensional lattice, pretty easy to visualize. If I were to ask you to visualize a three-dimensional lattice, you could do it too. You can imagine like a glass box with a bunch of marbles floating in it, right? But what would happen if I asked you to visualize a four-dimensional lattice? Eek, what happens there? Well, right now in the movies, Interstellar is back in theaters, so some of you might recognize this scene. When he enters the black hole, they wanted to simulate higher dimensional space, so they created this tesseract. And what's fascinating is that wasn't CGI, that was actually a practical set that he was moving through to look like higher dimensional space. Another way to represent it is this hypercube idea. But basically, humans can't really perceive of higher dimensions. And in lattice math, you can have as many dimensions as you want. You can have thousands of them. And it turns out computers can still handle them. We just can't visualize them. So in fact, level 5 ML-Chem has 4 dimensions. That's why I bring this up. It's not just a random, cool-looking visual. But again, the computers don't care. The more dimensions you add, it's just the same kind of math. And I'll show you what that looks like in a sec. But for now, we'll stick with 2 dimensions just so I can get across how lattices work. And as I said, these are not random dots. These are actually created in a very set way, so we can do some useful math with them. Because remember what I said earlier, with RSA, you have 2 large numbers, and then they get multiplied. You have to be able to try and factor them, which you can't. So that's that principle of getting those secret numbers that you could share. We need to get to a replacement with that using lattices. So how do we do that? So if you remember your grids from school, X and Y axis, we're going to zoom into the upper right quadrant over here, just the positive numbers to make it easier to understand. So you see the green axes, and we're going to stay up in the right. So any lattice is built on an axis. And how do you get those exact points? You get them with a matrix. So a matrix is basically, depending on the number of dimensions, it's these vectors that when you stack them together, they tell you how to create the lattice. All right? So in this case, you can see we have 1, 2, 3, 1, 3, and we have 2, 1. So if you make a matrix of those numbers, you are now describing this lattice. And if you keep repeating it and repeating it, you get this pattern that builds up through space. Awesome. That would be a good basis. Unfortunately, there's also the possibility of a bad basis. See, I can create a matrix like this and get the exact same lattice. Now we have a problem. Because if you were to try and do an operation, you'll end up in a different point in space if you have the wrong basis. So you need to know the good basis. And once you know that, again, it was 2, 3, and then, 1, 3, and then 2, 1. Once you know that, you can multiply that by a vector, okay? In this case, 2, 1. And what that says is, I'm taking this known basis vector, and I'm doubling it and moving it over 1. You see that? So you're able to get to a very specific point. Now, if we were to do this with the other bad basis, we'd end up somewhere else. So that's not useful for cryptography. We need to be able to generate large numbers. So knowing this and knowing that we can multiply, you're starting to see where I'm going with this, I think. We have the ability to have a matrix that describes a lattice and also a vector that we multiply by, and then theoretically we'll get an answer. So now, am I done? Do I multiply those two together and get a really large number, and then can you go backwards from that? Unfortunately, you can't. So you can't actually reverse that multiplication. With Gaussian elimination and inverse matrix, you can reverse. So we're still going to need to do something extra. And that something extra is where we're going with this talk. So remember when I said we have a matrix describing? It turns out for cryptography, the matrix is not just single numbers. It's actually polynomials. And they do tend to look very ugly. So for simplicity, we're going to pretend that they just map to those dots perfectly. I'm not going to make you try and do the math to figure out where to actually put those points in space. But I just want you to see how ugly the math can really get. Now, you see the matrix represents 2 dimensions because we just have the 2 basis vectors, right? But in theory, you could stack those numbers as high as you want. You can have it be 10 dimensions, 1,000 dimensions, it doesn't matter. It's all just math in the end. So right now, we're in this situation where we have A describing the lattice, how that grid plays out. And S is a secret that we're hoping for, a secret vector that we multiply to end up somewhere. And that somewhere we end up is that purple dot. Okay, but remember, this is reversible still. And if I were to ask you to find a point near that, there's something called the closest vector problem. And fortunately, the closest vector problem is going to be our friend here. And I'll explain why. So right now, we can't do anything with this. If I were to publish 2 of the numbers and hide one of them, you can reverse it. Useless for cryptography. But what if I were to add what's called an error? Okay, so this is where things get interesting. So you take A, which describes the matrix describing the lattice, you multiply it by some secret, and then you add E, which is a small error. So that little purple dot actually then gets shifted to that other point in space, that orange spot. And once you do that, you can no longer reverse this. So if I were to publish that spot, that orange spot, T, and publish the matrix describing the entire lattice, you can no longer reverse and find out how we got there. So now we're able to get a new basis for cryptography, a new 2 giant numbers, if you will. And the reason we can't do that is because there's something called the closest vector problem. And if you were to take a higher dimensional lattice and point anywhere randomly in it, finding the closest valid vector is computationally pretty much impossible. And we haven't found any way for a quantum computer to return it. So that simple little bit of trickery there, what we call learning with errors, is the secret behind generating these large numbers with lattice-based math. And that's really all there is to it. You now have the ability to generate keys for ML Chem. So again, A is a matrix describing the lattice. T is the final vector where you end up, that spot, and that becomes your public key. You publish that. S vector is the private key. That's the thing you multiplied. And the error vector with small coefficients is E. And I'm not going to be able to go into the full like reversals and all those equations, but just know that it is possible with the way that the equations fall out if you're the private key holder, to get back to where you started. So now with that level of knowledge, you should be able to fake in a cocktail party how you got these two numbers. So are we doing this just for post-quantum cryptography purposes? It turns out that ML-Chem is going to be a pretty powerful cipher going forward anyway. Pretend quantum computers aren't even a thing. If you look at the top there are charts of the levels of security. And remember I said level 5 ML-Chem, the highest level, which uses 4 dimensions. So that'll show you the sizes of the keys and the ciphertext and everything. But just to simplify it, I took one example of Kyber on the bottom, what it used to be called, and RSA, and I compared them. So you could see that, yes, ML-Chem is a larger public key, a larger ciphertext, but with computational resources getting better, that's not such a big deal. Now let's look at the actual performance though. Encapsulation-wise, RSA is still about twice as fast at encapsulating a message, but look at what happens with decapsulation. You have 100,000 versus 1,400. So it's like literally 100 times faster. Kyber's 100 times faster at decapsulating. And then for generating keys, I want you to imagine the world's fastest fighter jet. Multiply its speed by 3. That would be RSA. Kyber is the speed of light. It's like your brain can't even conceive of the speed jump there. That's how big that number is in key generation. So Kyber's key generation is going to be literally like going from a fighter jet to the speed of light. It's just a speed boost we haven't experienced before. So fortunately, the path forward with post-quantum cryptography is a good one, completely unrelated to the need of protecting against these systems. Now, because these ciphers were released, a bunch of actions have already kicked off. We took all these actions from the White House's NSM-10 roadmap. So this is a memorandum that tells the federal government what they need to do once NIST publishes the ciphers. And again, the ciphers are out, right? So now that that's out, we expect the private sector to greatly copy this. They're not going to reinvent the wheel. So already the federal agencies owe an inventory, which is a technical inventory of what kind of cryptography they're using in their organizations. That's already due. So we expect soon that the private sector will be asking for these as part of its regulatory processes. And you can see it filtering out in the industry. If you look at PCI DSS, they're already starting to be concerned with like keeping track of your cryptography and also literally tasking people with tracking cryptographic threats. And again, okay. I don't know. Okay, am I back? Okay. I can't think of a greater cryptographic threat than quantum, so you have to keep track of that. So already now, NIST also published its deprecation and disallowed scheduling. And by 2030, all current ciphers that are not post-quantum safe are going to be deprecated, which means by 2030, whether or not you believe in a quantum computer as ever coming, it doesn't even matter. You're not going to be allowed to use it. And by 2035, it'll be truly disallowed altogether. So the path to post-quantum is going to happen, whether the industry keeps up with it or not. This is just NIST now saying, throwing a stake in the ground. And I need you to know that even though it's a government thing and a US government thing, the whole world likes to do business with the United States. And all of the private sector in the United States likes to do business with the United States government. So whatever the United States government does based on this, I promise you everyone's going to have to do in some form or another going forward. One thing that might speed up the timeline, you might have heard of this Chinese paper that covered cracking encryption with D-Wave, and it had all these really overblown headlines. They were saying military-grade encryption cracked, and then you looked into it, and it turns out that the numbers they were cracking were not military-grade encryption. We're talking they cracked a 7-digit number as opposed to a 617-digit number, which is what military-grade encryption would be. So that also is a difference similar to the fighter jet and speed of light example I gave before. So no, that's not exactly a thing. Just wanted to point that out in case it comes up. So we're going to need to start this inventory process, this migration, and these are just the basic 4 steps to at least begin this process. You have to really understand how data moves in your environment. You have to understand the cryptography in use and get that technical inventory we discussed. Then you have to start worrying about abstracting cryptography out. Sometimes people write code, for example, and it's baked in, and then you have to blow up your code and start all over again. You're going to want a more modular approach going forward. And then the goal is, of course, crypto agility. As you prepare to implement new technology like PQC, you want to make sure that doesn't cause disruptions. So that's where that kind of use of agility comes in. So I just wanted to leave you with that visual. And I think I have like 2 minutes or so to answer a couple questions before we move on. So if anyone has any. I can't believe I was able to let a hand go up with these lights.
Since we know that actually what that was one stack for the how the integration this class related to that related will be one for the
Yeah. So the question is basically we're going to have multiple standards, right? Like, should you basically wait? Should you? So we expect to have lots of different types of cryptography and use around the world, and we expect them to be following the paradigm of what you've already seen in your browser. Like, if you were to look at, if you were to ever be part of an audit for cryptography in the past, or a pen test or something, you notice that browsers and websites support a lot of ciphers. That's always been the model. Like, oh, we can handshake to this, handshake to that, and then we have this customer that needs this one and that. That's what I expect, sort of like a cipher soup going forward in the future. And depending on who you do business with, you're going to want to be able to support as many of those as possible. I would love it if we would start with hybrid post-quantum cryptography, this idea of what AWS is already doing, what Apple's already doing, where you take ECDSA and you wrap it, and you have post-quantum cryptography. That way, if post-quantum fails for some reason, there's a flaw, whatever, you're no worse off because you still have the tried and true. So hybrid would be great, and it's a minimal performance hit. And like I said, hardware is getting better all the time. But yeah, that's definitely going to happen. So I expect within a year, one of the other ones will probably be out too. And if someone has a 2-word question I could answer with 3 words, we could probably take it. And if not, as I like to say, I'm pretty easy to spot in the hallway. I'm the head floating above the other heads. So you'll be able to catch me, and feel free to ask. I'd be happy to answer. Okay, so with that, thanks everybody. Thank you.